Thanks very much for inviting me, and thanks for coming to this talk. So the talk that I'm going today is perhaps slightly away from the topic of the main theme of the conference, but there's some curious interaction with additive combinatorics in the sense that early on in a joint work with Yifan Jing and Sutik Roy, we use some model theory to prove a sum product result for polynomial, and then now we're applying that result back to solve a question that is perhaps of pure interest to model theory. So let me start slowly and perhaps remind you of some of the terms in model theory in case you forget them or you have not seen them before. So let me start with the very basic notion. So a structure in the sense of model theory. So this is just a triple consists of an underlying set a family of relation, and a family of function. So A over here is just a set, and for each I, so a relation is simply a subset of Cartesian product of the underlying space, right? And for such thing, we will call this an Emery relation. A function is, and for each j, fj is a function, so it is a function from the n-dimensional space to A, and we call such thing an Emery function. So let me give you some example of a structure. So an example that you can try to keep in mind is you can look at the field of complex number. So in this case, you only have two binary relation and two binary function and no relation, right? And this is the structure that we will care about very much for today. And in some way, you can think of the notion of the model-theoretic structure as a generalization of field, right? And another structure you can think of, okay, so I would also denote this by C tilde. And another structure is like the order field of real number. So in this case, you would the ordering would be a binary relation, right? And other structure that we will look at today is like the field of complex number together with a polynomial, where P is a complex polynomial in two variables. After the structure, the next notion that we have a model theory, which is analog of a polynomial. So analog of that could be a term function. So a term function, so here we allow parameters. So this is obtained by composition the basic function. And an example, so let's take an example, some example of that. So for example, x squared plus pi y cubed. So this is a term function, right? In the structure of a complex number with addition and multiplication. And you can see that you can get x squared by taking x multiplied with x, right? And y cubed as by repeating multiply y together, and you can put them together under addition, right? So another example is, let's say e to the x plus y. So this is a term function in the structure of a complex number together with the exponential map, right? So you can see that we have a more flexible notion than polynomial, right? So the next thing we want to look at is an analog of an equation, and that is given by the notion of an atomic definable set. So this is the set satisfying an equation or a relation that involve a term function. So let me once again give you some example. So example is so if you are trying to look at the set of on the pair x, y, z, let's say in C cube, such that z is equal to x squared plus y squared, right? This is definable in the field of complex number. And if you are looking at the set of on x, y, z, let's say in R cube, such that z squared is smaller than x squared plus y squared. So this is definable in the order field of real number. And as you can see, so by allowing the relation, a lot of times we can deal with object that is a bit more general than equation. So for example, like we are allowing a solution set of inequality.
So technically speaking, equality is not a relation in C delta, right? Right. You can still use it in terms of.
Right. So equality is in logic, it's called a logical symbol, and you get it for free. Yeah. All right. So and the next notion is the notion of a definable set. So this is obtained from the atomic definable set. By application of Boolean combination and projection. So an example is, so if you're looking at the set of on the element x, such that there exists y, x is equal to y squared, and there exists z, x is equal to 2z. So you look at x in z, so that this is the case. So this is definable in the ring of integer, right? So so you can think of definable set as a solution set of the first order formula, right? So definable set is in some way the logician counterpart of algebraic set, but in some way we are allowing some more generality, and because of that, sometimes it behaves more flexible. We have some more flexibility.
So you can't have infinitely many.
Yes, so that's right. So in some, yes, or you cannot have infinitely many conjunctions, but that existential formula, you can think of it as infinite union of many things that satisfy this kind of equation. So in that sense, you allow a little bit in between finite and infinite. Okay, so these are the extremely, okay, so these are something that you probably could see in any first course in logic. So yes.
So is there any projection here, or what's the example of a projection?
So a projection over here is because if you're looking at the pair x equal to y squared, right? So that is a subset of Z2, right? But to saying that there exists y means you are projection onto those that only involve x coordinate. So existence and projection, in some way, they are more or less the same. All right, so these are definable set. Okay, so let me start talking about the main notion, the real notion that we were looking at today. So suppose you are given two structure A1 and A2 with the same underlying set A. So you can think of A1 as A together with involving a bunch of relation and function, and A2 is also the same. So we would say that A1 is a reduct of A2. If every subset of AM definable in A1 is also definable in A2. So you can think of this as saying that A1 consists of at most as much data as A2. Once again, let me give you some example. So the example is, so if you're looking at the complex number together with, let's say, a polynomial pxy. Okay, so let's say xy mapping to x squared plus y cubed, right? So this is, okay, let me try x squared plus y squared. So this is a reduct of the full field of complex number. And probably it's not too hard to see why that is the case, because any term function that appear in this structure, right, it would already be a term function that appear in this structure, right? So every set that is definable here could be definable over here, right? So it turned out to be also the case that, so more seriously, it turned out that the field of complex number is also a reduct of this structure. So complex number together with x squared mapped to x squared plus y squared. Right. Essentially, somehow you need to manage to recover back both addition and multiplication from this. And perhaps let us be super brief about it. So, so why that is the case? So first of all, you can see that the map x mapped to x squared is still definable in this structure, right? And moreover, you can recover back x plus y by making a following observation. So z is equal to x plus y, right? If and only if there exists x prime and there exists y prime, right? Such that x is equal to x prime square, y is equal to y prime square, and z is equal to x prime square plus y prime square. So we can see that you can recover x plus y from x squared plus y squared and this squared, right? And to recover back, okay, so if you can recover plus, you can recover back minus, and you can recover multiplication by a rational number, and so on and so forth. And then finally observing that xy is equal to x plus y altogether square minus x squared minus y squared divided by 2, right? And from here you can recover back multiplication, right? Okay, so with that, let me state, maybe one more notion before I state the main problem that we are looking at. So another notion is that we were saying that A1 and A2 are interdefinable. If one is a reduct of another. So that is to saying that they consist of exactly the same data. So the problem that we are interested in is the following. So we are interested in the problem. So we want to classify on the reduct of the field of complex number up to interdefinability. And well, so this is the problem, but well, if not, say something interesting. So this is a problem that we want to look at. So today, I want to focus on a special case of this problem where we consider a reduct of the form complex number together with a binary polynomial. I would like to prove the following theorem. So, so the theorem is the following. So this is by Gaspar and me. And so theorem saying that each such reduct is interdefinable of exactly which one the following. So first of all, the first possibility is it contains the full data of the structure. So that could be the field of complex number. The second possibility is that could be the additive group of complex number together with perhaps certain extra vector space structure. So multiplication by lambda, where lambda range through a field F, where F is a subfield of the field of complex number generated by apples at two elements. And the third possibility is you have the complex number to almost together with multiplication. But this is a slight possible variation of multiplication where you allow the twisted multiplication, which is defined by, which is given by x twisted multiplied with y. So this is defined by x minus b multiplied by y minus b plus b. So it's a slightly variation of multiplication. So there's 3 more possibility. Possibility number 4, it is the complex number together with a unary polynomial. Where the degree of u is greater or equal to 2. And 5, the complex number together with a linear polynomial x going to ax plus b, and x going to, and the inverse of this x going to x minus b over a. And the last possibility is just the set C itself with no structure. Okay, so perhaps this, and I would argue that in some way, this is an indication that eventually we'll get some reasonable classification of on the reduct of the field of complex number. And in some way, we already we have in mind what should be the correct statement, but perhaps it will take another while for us to get into this classification. And maybe one more thing I want to mention is, so even though this question, so this question looked like a very easily to state question. Suppose you know just a few notions in model theory, but this problem was not was completely out of reach until the last year, right? And then one of the major new development was this resolution of the restricted trichotomy conjecture, which allow us to obtain this classification. All right. So for the rest of the talk, I would like to sketch the idea of a proof of this result. But so before that, perhaps let me make one comment about the underlying idea of this result. So,
sorry, can I ask a question about what do you mean by generated by the most 2 elements? So it's a field, it's a subfield, right?
Yes.
So it contains 0 and 1.
Okay, yeah. So generated by at most 2 element in C. So it's a subfield that is generated. Yeah. So if you choose the 2 elements to be 0 and 1, right? That subfield would just be rational number.
Right.
Right. But so different choice of 2 elements, right? It could give us different field.
So Q is generated by 0 elements, right?
Right, but you can also choose 2 elements like
Yeah, sure.
by at most 2 elements.
So how is Q generated by 0 elements?
Well, it's the field generated by
Okay.
means that it contains 0.
Right, so Q is generated by 0
Okay,
elements.
so you don't count 0 and 1. I see. It's my mistake. I see. I understand that.
In 5, do you know, as you vary A and B, do you get different?
Right, so as you vary A and B, as long as this pair are the same pair up to permutation, you get different structure up to interdefinability. Right, so all of these are in some way unique, right? So we can show that that's the case. Okay, but so let me mention something about the underlying idea of this proof, which is maybe perhaps some conceptual interest. So the underlying idea of this proof is that somehow group structure is very robust. So maybe one thing okay, so this is not obviously just a short list, right? There are quite a lot of items in this, right? But you might wonder, okay, why can there be even more, right? Given that if you put Reduct, you can put many different things, right? So why you can have such a short list? And the reason that you have such a short list is because it comes from the fact that group structure and maybe field structure, they are pretty robust. So they are robust in the sense that so from group-like and field-like data, we can often recover a group. And this idea is very central in model theory. So, and if you want to find one keyword, you look at the word group configuration. So this idea that, okay, so this idea is pretty central in model theory, but it also appears in additive combinatorics. So an example that, so maybe let me to mention some example. So an example is, say, Feynman theorem. Right? So Feynman, which saying that if you have a subset of the integer, and in some way behave like a subgroup, right? So the size of A plus A is smaller than K times the size of A. Then A can be covered by an arithmetic progression that is not too large. That is not too large. Okay, so arithmetic progression is essentially that it's just a segment of a translate of a segment of a subgroup, right? So this is saying that, well, if you have something that look a little bit behave like a subgroup, it must actually come from a subgroup. And in fact, to solve so the solution of, okay, the way we prove this theorem, some way we need to use this is in application of this Gauss principle. Okay, so with that, let me describe to you the proof. Yes.
Is it easy to see why one should not expect any of these reducts to have a relation? They all have functions, no relations.
Exchanging a relation and function in model theory is not too hard, right? So if you have addition, you can also replace it with the graph of addition. And that is from the model theory point of view, they are exactly the same.
And somehow these are the only sort of relations that.
Right. So, and in some way that come from the fact that the group are robust, right? So if you have something that is like a group and you have two different groups, then you are forced to go up on the way and you have a few. Yeah, so that is sort of like the idea that is happening over here. Okay, so perhaps let me describe to you the idea of the proof and so the proof has two steps. So in the first step, so this is a kind of like a cross classification. And the tools that we use over here is, so we use tools from model theory. Include the idea from geometric stability theory. And the solution of the restricted trichotomy conjecture. And what we are going to show is that, so to show that a non-trivial reduct must be related to a one-dimensional group. Or a field. So we somehow saying that, oh, if you are forced to be related, either you are really trivial or you are forced to just be a one-dimensional group, or you are forced to be a field. But this relation is a rather loose relation, right? It's not yet a condition, a precise statement like this. And for that, we need to require step 2, which is more or less, which is the phi classification. And what this has 3 different items. So in 2a, we're saying that when this okay, so that we could let A to be a reduct of the field complex number, and we say that when A is related to a field, then A is forced to be the field itself. So A must be interdefinable with the field, with the full field. Or in other words, we are in case 1. And in 2b, so when A is related to a group, a one-dimensional group, then we are in the case 2 or in the case 3. And finally, and this is 2b is the case that we would use the tools in additive combinatorics. And finally, in 2c, in the trivial case, we want to show that we are in 4, 5, or 6. And my goal is to explain to you, okay, in the interest of time, perhaps I would try to explain step 1 and step 2b.
So 4, 5, and 6 are considered trivial?
Yes, 4, 5, and 6 are considered trivial in the sense of geometric stability theory.
Okay.
So we have a specific notion called trivial.
Oh, I see.
Yeah. Yes. So perhaps that's slightly confusing, but any other question? Okay, so I will focus on 1 and 2b. The first step is to get of this cross classification. And perhaps to explain this choice, so the tools of one is maybe completely model theory, but I hope that this kind of concept is somewhat interesting, and maybe I would hope that it will take a chance to introduce some tools in our area which might be useful for other purpose.
Sorry, I have a specific question. Maybe I misunderstood. So what you're classifying are reducts of C with a polynomial, or reducts that are of C that take the form C in the polynomial?
Yeah, it's just the reduct of the pure set C together with one polynomial, right? Because if we take the whole C and we add the polynomial is already contained in C itself.
Yeah. So that's why I think, like, if you take P of X Y to be X squared plus Y squared, for instance,
Right.
then doesn't this classify all reducts of the complex field? Like, it solves your problem. The question you stated.
So for example, if we are taking the polynomial Pxy to be X squared plus Y squared, right? Then that structure, it could fall into case one, right? But if you take another polynomial, for example, C together with X plus Y, right? That would fall into case two.
So okay, so this list 1 through 6 are reducts of just the complex field,
Right.
C tilde,
Right.
which are of the form C comma polynomial of some shape.
That's right.
I see.
Yes. Yes.
Thank you.
So yes, thanks for the question, for clarifying question. Yeah, so hopefully eventually we will be able to classify all reducts. But today, in some way, this is just one step.
Yeah, I'm just trying to understand the same. Yeah, thanks. Yeah.
Thanks. Yeah.
And
Okay.
sorry, just because it's on the same topic, do you have an example of a reduct that's not in here?
Do we have an example? We have not here. Yes, we do. Right. So an example that is take complex number together with the relation z squared is equal to x squared plus y squared. So this turned out to be a cover of the field instead of a field itself. So the eventual classification would be something like, well, every reduct of the field complex number is just a cover of a list of example plus some noise. So that is hopefully the final result.
And the length of the list would depend on the number of parameters or the number of your formula. What will the length depend on?
So the length, there's not that many more items in the list. So how, other than this example,
No, but then you have this c squared equals x squared plus y squared.
okay. So
what do you expect to be the truth?
so this would be a cover.
Yeah, I understand. Okay, never mind.
So maybe the length of the list. So other than this item, there could be one more example that comes from elliptic curve. And that are the basic example. And then all the other example are cover of the basic example, adding some noise. So that will be the final result that we will have. Okay, so let us discuss the proof of step one. So in step one of this cross classification. So by the way, so may I ask, should I stop at 50 or should I stop at
55 or so.
Oh, okay, thanks. Yeah. Okay, so in the cross classification, the first observation is that if A is a reduct of the field of complex number, then A is must be strongly minimal. And I will explain what does it mean by strongly minimal. First of all, it's an observation. So if you are looking at an algebraic family of subset of complex number, then an observation is that there could be a uniform bound on the size of the finite member of the family. So let's say if I'm looking at the family of solution set of ax squared plus bx plus c is equal to 0, right? Where I let a, b, c range over complex number, right? So if you think about it, so when a, b, and c when are on 0, right? The solution set of this could be the whole complex number, right? In on the other case, you would at most have 2 elements in each of the member family, right? So there could be a uniform bound on the size of the member of the family, right? Similar phenomenon, it also applies if you replace algebraic family by definable family. But the difference is that for a definable family, so every member of the family can be finite or cofinite. But the size of the finite or cofinite, there is a bound on the size of finite or cofinite. And that property is called strongly minimal, right? So the field of complex number is turned out to be strongly minimal. And because of that, any reduct of the field of complex number is also strongly minimal, because every definable family in a reduct is already definable in the weaker structure, right? So one of the insights of modern model theory is that in many settings, one can develop a dimension theory. And in particular, strongly minimal is a setting where one can develop a dimension theory. And using the dimension, we can classify, we can understand the property of many of these structures. To say that precisely, okay, and because of that, okay, so maybe I could skip some step. So as a consequence, there could be a dimension. So there is a dimension on A. And under that dimension, so this dimension could satisfy a bunch of basic properties. So for example, finite set could have dimension 0, right? And the dimension of the set A would be equal to 1. The dimension of A squared would be equal to 2, right? And so on and so forth. So we would say that a definable subset C subset of A squared is a plane curve if the dimension of C is equal to 1. And we say that C, a plane curve is non-trivial if both projection from C, both projection from C to A are finite to 1. So if you have a family of plane curve, a definable family of plane curve, so let's go with C, B, where B range over set Y of non-trivial plane curve. Is called faithful. If taking any two members of this family, the intersection are finite. For P different from P prime. So that means that if you are looking at such family, they are all different from one another, up to finitely many elements. And the dimension of such family is just the dimension of Y. Right? So dimension of Y, the dimension of the family. So okay, I should erase that. I should just. So the following is a classical result by Zuber and Khrushchevsky. So, so this is a fact by Zuber and Khrushchevsky. So if A is strongly invoked, then the possible dimension of a faithful family of non-trivial plane curve is exactly one of the following. So first of all, it can be every family of faithful non-trivial plane curve must have dimension 0. Second possibility is the only dimension possible is 0 and 1. And the third possibility is every natural number can be a possible dimension of a non-faithful family. And an example that one can think of this is if you are just looking at the structure that consists of only the set of complex number, and you're trying to look at what are the possible non-faithful plane curve. In some way, there's only one of them, like the diagonal, right? Because the only thing that you can say is equality, right? So the only thing that you can have is diagonal, and that because of that, that is a one-dimensional family, right? So the second example is when, so for this, if you have a complex number together with plus, you can have a zero-dimensional family. So for instance, that family, but you can also have a one-dimensional family, namely the family of y is equal to x plus b, right? But if you are looking at the complex number together with addition and multiplication, you can have family of higher dimension. Right? So if you're looking at y is equal to ax, okay, so x squared plus ax plus b. Right, so this is the family of on the parabola. This is a two-dimensional family, right? And similar, you can construct higher family, right? So this result is saying that somehow you are broken up into three possibilities, right? Roughly corresponding to something that's trivial, or just corresponding to a one-dimensional group, and or it corresponds to something that looks like a field, right? And it turned out that so it turned out. So let me mention the second case, which is the case that eventually is we will apply the combinatorics. And in this second case, a fact which comes from geometric stability theory is that not only, so by this very coarse data of something that look like a group, namely only in terms of dimension, you can indeed recover a one-dimensional group. So this is the fact. So we're saying that. So suppose I is in case 2. So that means that the dimension is either 0, the dimension of any faithful non-trivial family of plane curve is either 0 or 1. Then there is indeed a group. Then there is a strongly minimal group G plus which is interpretable in I. Okay, so this is just slightly more variation of the notion of definable in I, such that the following two conditions is satisfied. Such that, so first of all, I is in a finite to finite correspondent with this group. With this group, and second, the induced structure on the group is close to being a pure group. So that is to say that in the second case, more or less, you are getting back a one-dimensional group, right? And it turns out that in the third case, well, you would get back a few, right? A few. But to show that that is known as the restricted trichotomy conjecture, and we are only know the solution by my collaborator Gasso the last year. Okay, but perhaps in the interest of time, maybe let me just take this case that you are having a group, and that you know that the structure A is very much closely related to a group, right? And my goal could be trying to showing that my goal would be trying to show that it must be the example 2 or example 3. Right? So my goal would be trying to show that it is just these two examples. So how do we do that?
So that's the part that uses combinatorial.
Yes, so that is the part that we would use combinatorics. Yes. So how do we do that? Okay, maybe I should. In a step 2b. And let us just focus on a very special case, right? Say we have one-to-one correspondent to a group that we know, right? So just complex number together with addition. Right, so what will happen in this situation? So what we know is that we have complex number together with this polynomial. It is closely related in a one-to-one direction with complex number together with addition, right? Because the structure that we have on complex number together with addition by this property that the induced structure is very close to a pure group, The only thing that you can have over here would be something like would be coset of this group itself, right? So if you're looking at the graph of this polynomial, it could be more or less in a one-to-one correspondent with the graph of y is equal to z is equal to ax plus by plus a constant c. The solution set of this. Yep. And so if you are looking at this, you would be able to choose a very large set B, a large finite subset of the complex number, such that if you're looking at A times B plus B times B plus C, so you look at the image of this under this polynomial, the size does not grow too much. So let's say that this is still smaller than or equal to the size of B to the power of 1.1. Right? But because under this correspondence, one could be able to find a set A, which is a subset of the complex number, such that if you are applying polynomial to A, the size of this is still not growing too much. And using the kind of result from additive combinatorics, we would be able to reduce the structure of such polynomial. Let me continue to write here. So by a result by Ching, Roy, and myself, we would be able to show in that Pxy is either of the form f applied to a constant of ux plus another constant of uy, or f applying to u to the mx, u to the ny, where f and u, these are unary polynomial, right? So we have a strong control on what kind of polynomial it is, right? It's not yet the thing that we want, right? We want something like a linear polynomial, but that can be obtained by playing around with this a little bit more, and then we will be able to force to conclude that Pxy is either linear or twisted multiplication. And that brings us into the situation of 3 and 4. Okay, so thanks very much. I guess that's all I have today.
Questions for me?
Yes. So what could this result that the polynomial has to take this shape? Is this some sort of sum product, or?
Yes, so this is somewhat a result in the form of the Legge-Ronja theorem, but for symmetric set. To show this, we use Legge-Ronja plus some result in omnimality to do some control to get this result.
So I vaguely remember a theorem by Shushovsky which says that if you have an algebraic matroid with enough structure in it, then somehow from this structure emerges a one-dimensional group over your ground field.
Right.
Since you were mentioning elliptic curves earlier, I was wondering, is that related to what you're doing?
Yes. It's more or less this fact that over here, right? So if we have this one-dimensional family of length curve, one could be able to obtain a one-dimensional group in that setting. And the only one-dimensional group that we know are either additive group, the multiplicative group, or an elliptic curve. So that is, so I think that that's essentially this fact.
Okay, any further questions? If not, then let's thank you again. Thank you.